You think you understand motion. You don't. Here's a simple question. What happens if you chase a beam of light? You run after it faster, faster, as fast as you can possibly go. Does the light slow down? Does it look different? Does anything change? Go ahead. Try to answer that. You can't. Not really. Because the answer isn't just surprising, it demolishes the entire framework you use to understand reality. Space, time, motion, cause and effect, all of it falls apart the moment you seriously ask this question. Einstein asked it when he was 16 years old. What would a light beam look like if you could catch up to it? That question, that one simple question, led to special relativity. It revealed that space and time aren't what you think they are, not approximately wrong, completely wrong. Right now, light is hitting your eyes at 299,792,458 meters per second. That's exact. Not a measurement with error bars, that's the definition of the meter. And here's the thing that should bother you. No matter how fast you move toward that light or away from it, it hits your eyes at exactly the same speed. Exactly, to every decimal place we can measure. That's not intuitive. That's not reasonable. That's not how anything else in your experience works. When a car drives toward you, it approaches faster than when you're both standing still. Speed adds. Velocities combine. That's common sense. Common sense is wrong. Let's build this from the ground up. Start with something you can actually do. Imagine you're on a train moving at 50 meters per second. You throw a ball forward at 10 meters per second relative to you. How fast is the ball moving relative to someone standing on the ground? Easy. 60 meters per second. Speeds add. This is Galilean relativity, and it's been obvious since humans started moving in vehicles. Now do the same thing with light. You're in a spaceship moving at half the speed of light, 149,896,229 meters per second. You shine a flashlight forward. The light leaves the flashlight at 299,792,458 meters per second relative to you. Question: how fast is that light moving relative to someone floating in space watching you pass? Your intuition says 449,688,687 meters per second, half the speed of light plus the speed of light, just like the ball on the train. Your intuition is wrong, dead wrong. The answer is 299,792,458 meters per second. Exactly the same speed. The person watching you measures the light from your flashlight moving at exactly the speed of light, not faster, not slower. Exactly the same speed you measured. This is what the Michelson-Morley experiment showed in 1887. They tried to measure Earth's motion through space by comparing the speed of light in different directions. Earth moves around the Sun at about 30,000 meters per second. Light should travel faster when we're moving toward it and slower when we're moving away. That's how everything else works. They measured it. The speed didn't change. Not even a little bit. They improved the experiment. Measured again. Still nothing. The speed of light was the same in every direction. People tried to explain this away. Maybe Earth drags some medium with it. Maybe the apparatus contracts. Maybe the measurements were wrong. No, the measurements were right. Reality is weird. Now here's where it gets interesting. If the speed of light is the same for everyone, and speed is distance divided by time, then something has to give. If you and I both measure the same speed for light, then we must disagree about either distance or time. We disagree about both? This is Einstein's insight. In 1905, he started with two postulates. First, the laws of physics are the same in all inertial reference frames. Second, the speed of light is the same for all observers. That's it. Everything else follows mathematically. You're in that spaceship moving at half the speed of light. I'm floating in space watching you. You shine your flashlight forward. We both measure the light at 299,792,458 458 meters per second. But think about what that means. From your perspective, 1 second passes. The light travels 299,792,458 meters. From my perspective, more than 1 second passes. Your clock runs slow. Time itself is passing more slowly for you than for me. I see the light traveling the same distance while more time elapses. The speed comes out the same because both the distance and time are different for us. We can calculate exactly how much using the Lorentz factor. Gamma equals 1 square root 1v squared divided by c squared. At half the speed of light, gamma is approximately equal to 1.155. For every second on my clock, only about 0.866 seconds pass on yours. Your clock runs at 86.6% the rate of mine. This is time dilation. It's real, measurable, confirmed. Muons prove this. They're particles created when cosmic rays hit the upper atmosphere. They decay with a half-life of 2.2 microseconds. At 98% the speed of light, they should only travel about 650 meters before half decay. The upper atmosphere is 10,000 meters up. We shouldn't detect many at sea level. But we do. Lots of them. Why? Time dilation. At 0.98 C, the Lorentz factor is about 5. Their 2.2 microseconds is our 11 microseconds. They travel far enough because time is passing more slowly for them. From the muon's reference frame, their clock shows 2.2 microseconds. But the distance is contracted. Length contraction. The 10,000 meters shrinks to about 2,000 meters. They make it because the distance is shorter. Both perspectives give the same answer. The muons reach the ground. But the explanation depends on your reference frame. GPS satellites prove this every day. They orbit at about 20,000 kilometers, moving at roughly 14,000 kilometers per hour. Time dilation slows their clocks by about 7 microseconds per day. But they're in a weaker gravitational field, so general relativity speeds their clocks by about 45 microseconds per day. Net effect, their clocks run fast by about 38 microseconds per day. 38 microseconds. Light travels about 11,400 meters in that time. If we didn't correct for relativity, GPS would accumulate errors of over 11 kilometers per day. Your navigation would be useless. We correct for this. The satellite's clocks are set to run at a different rate before launch. Every time you use GPS, you're proving relativity is correct. Now back to chasing light. What actually happens? Newton would have said, you can catch up, keep accelerating, eventually match the light's speed, then exceed it. From your perspective, the light would slow down, stop, then move backward. But that can't happen. The speed of light is always c relative to you, no matter how fast you're moving. Why not? As you accelerate, as you approach the speed of light, time dilation becomes extreme. Your clock slows dramatically. Length contraction becomes extreme. Distances shrink in your direction of motion. Your momentum? The formula P equals mv only works at low speeds. The relativistic formula is P equals gamma-mv. As v approaches c, gamma approaches infinity. Your momentum approaches infinity. To accelerate further requires more and more energy. At the speed of light, you'd need infinite energy. You can't reach it, not because something pushes back, but because the structure of space-time prevents it. Think about what this means. The speed of light isn't just the speed light happens to travel. It's a fundamental feature of space-time, a speed limit built into reality itself. Light travels at this speed because light has no mass. Anything with no mass must travel at this speed. Anything with mass must travel slower. As you accelerate toward the speed of light, the universe contracts in front of you. At 99.9999% of c, the distance to a star 100 light-years away contracts to less than half a light-year. From your perspective, you could travel there in months. But the light is still moving away from you at exactly c, always. No matter how close you get to light speed, you measure light speed as c. From the perspective of someone watching you, your clock is running extremely slow. You're experiencing less time. The light is moving away from you at c, and you're moving at just under c, so the gap closes very slowly from their perspective. Both perspectives are correct. Both give consistent answers. The journey takes less time on your clock than on theirs. The distance is shorter in your frame than in theirs. The speed of light is c in both frames. Maxwell discovered this before Einstein, though he didn't realize it. In the 1,860 seconds, Maxwell unified electricity and magnetism. His equations predicted electromagnetic waves should exist and travel at one square root, epsilon 0 mu 0. When you plug in the numbers, 299,792,458 meters per second, the speed of light. Maxwell's equations don't care about your reference frame. They give the same answer regardless of how you're moving. This bothered people. The speed should depend on motion. Everything else does. But Maxwell's equations said no. Einstein took this seriously. If the speed of light is invariant, then space and time must be relative. Hermann Minkowski showed in 1908 that special relativity is best understood geometrically. Space and time aren't separate, they're part of four-dimensional space-time. The space-time interval equals c delta squared minus delta squared minus delta squared minus delta squared is the same for all observers. We might disagree about how much is space and how much is time, but we agree on the total. Time is a dimension mixed with space. The speed of light c is the conversion factor between space and time. Here's the truly wild part. You're always moving through space-time at the speed of light. Not through space, through space-time. Your four-velocity through four-dimensional space-time has magnitude exactly c. When you're sitting still, all your motion is through time. You're moving through time at maximum speed. When you start moving through space, some of your motion through time gets rotated into motion through space. You move through time more slowly. This is time dilation. Photons move through space at c, which means they don't move through time at all. From a photon's perspective, no time passes ever. A photon emitted 10 billion years ago and absorbed by your eye right now experiences zero elapsed time. Emission and absorption are simultaneous from the photon's reference frame. The universe has no age from light's perspective. All of cosmic history is compressed into a single instant for anything traveling at the speed of light. But there's more. Special relativity only works at constant velocity. The moment you accelerate, it breaks down. Einstein spent 10 years figuring out what happens with acceleration in gravity. The answer: general relativity transforms everything. Einstein's thought experiment. You're in an elevator, in deep space, it accelerates upward at 9.8 meters per square second. You drop a ball, it appears to fall to the floor. But it's not falling, it's staying still while the elevator accelerates around it. Now you're in an elevator on Earth. The cable snaps. You're in free fall. You drop a ball. It floats next to you. Gravity has disappeared. Einstein's insight. These are equivalent. Acceleration and gravity are the same thing. This is the equivalence principle. You shine a laser horizontally across the accelerating elevator. The beam curves downward. While the light crosses, the elevator accelerates upward. The light travels straight through space, but relative to the elevator, it curves. By equivalence, light must curve in a gravitational field. Einstein predicted this in 1915. In 1919, Arthur Eddington measured it during a solar eclipse. Stars near the sun appeared shifted. Their light bent by 1.75 arcseconds, exactly as predicted. But light always travels in straight lines. Always. So if light curves near the sun, it's not the light bending, it's space-time itself. The sun curves space-time around it. Gravity isn't a force, it's the curvature of space-time. Objects move in straight lines through curved spacetime, and those straight lines look curved to us. Einstein's field equations. G mu nu equals 8 pi g divided by c to the power of 4 t mu nu. Left side, curvature of spacetime. Right side, distribution of mass and energy. Matter tells spacetime how to curve. Spacetime tells matter how to move. Push this to the extreme. Make the object massive enough, compact enough, and light can't escape at all. The curvature becomes so severe that all future paths lead inward. This is a black hole. The event horizon is a point of no return in spacetime. Cross it, and every direction you can move points toward the singularity. The future, your future, light's future, points inward. What happens if you chase light near a black hole? You can't hover near the event horizon without enormous energy. At the horizon itself, you'd need infinite thrust. You'd have to move at c just to stay still. Fall in instead. You cross the horizon. From your perspective, nothing dramatic happens. You're in free fall. You shine a flashlight. Light moves away from you at c, as always. But now you're inside. The singularity isn't a place in space, it's a moment in time. It's in your future, unavoidable as tomorrow. You can't avoid hitting it any more than you can avoid next Tuesday arriving. From outside, someone watching sees you approach the horizon, appearing to slow down, time dilating more and more, freezing at the horizon asymptotically, never quite reaching it. Both perspectives are real. You fall through infinite time on your clock, they see you take infinite time on theirs. This is curved space-time. We've detected black holes. LIGO detected gravitational waves from merging black holes in 2015 ripples in space-time itself. The signal matched predictions to incredible precision. In 2019, the Event Horizon Telescope imaged a black hole's shadow. The size, shape, brightness all matched general relativity. General relativity has been tested at every scale: GPS satellites, binary pulsars, black hole mergers, cosmological observations. Every test confirms the theory. So what happens when you chase light? The answer depends on where you are and how spacetime is curved. But locally, light always moves at c relative to you. The structure of spacetime determines the paths light takes. But the fundamental principle holds. The speed of light is invariant. Why does any of this matter? Because it reveals something profound. Space and time aren't containers for physics. They're dynamical, responsive, curved by mass and energy. The universe isn't a stage. The universe is the events happening in space-time that bends and flexes. And light maps out the geometry of space-time itself. Because light always travels at c, every light beam is a geodesic, a straight line through curved space-time. By watching how light moves, we measure the curvature. This is what happens when you take one fact, the invariance of the speed of light, and follow it to its conclusion. You don't just learn about light, you discover the structure of reality itself. Why is c invariant? Why is there a speed limit at all? This is where the chain ends. We have a description, a mathematical framework that perfectly describes space-time. We can calculate, predict, test. Every test confirms the theory to absurd precision. But why space-time has this structure, we don't know. That's not a failure. That's what a fundamental theory looks like. You reach bedrock. There's nothing underneath. You asked, what happens if you chase a beam of light? Here's the answer. You can't catch it. Ever. No matter how much energy you use, the light recedes from you at exactly c. Not because you're not trying hard enough, because space-time itself forbids it. And that's not a limitation. That's a revelation. The speed of light isn't a speed. It's the structure of space-time. It's the ratio between space and time, the speed at which causality propagates, the conversion factor in E equals mc squared, the cosmic speed limit that keeps the universe consistent. Einstein asked that question at 16. He realized the premise was impossible, and working out why revealed the true nature of space and time. We live in a relativistic universe. Time dilation, length contraction, the invariance of c, these aren't curious facts about light, they're fundamental features of reality. Every moment of your life, you're living special relativity. Every time you check GPS, you're proving Einstein right. Every photon hitting your eye travels at exactly c, always unchanging. This is where physics lives, in the gap between what you expect and what actually happens, between what makes sense and what's true. You chase a beam of light, and it doesn't slow down. Your intuition fails, and in that failure, reality reveals itself. Not comfort, not simplicity, truth.